Dear students, welcome to all of you. 2022 Units 5 and 6 Numerical Analysis CC-14 Semester 6 B.Sc Mathematics Honors University of Calcutta. CC-14 question paper Unit 5. Question 12. For a system of n equations in n unknown xi I equal to 1 to n with increment 1, and let xik be the kth iterated value of the variable xi, and x for the kth iteration equal to x1 k, x2 k, xn k whole transpose t whole transpose be the solution vector obtained at the kth iteration, and xi equal to xi1, xi2, xn whole transpose be the exact solution of the system of equation. If aii not equal to 0 for I equal to 1 to n with increment 1, and n is equal to maximum over I equal to 1 by modulus of aii summation over j equal to 1 to n j not equal to I modulus of ij, can prove that the estimate of the absolute error of Gauss-Seidel iteration method can be represented by this, where norm denotes a norm of a vector and aij be the coefficient of I, the ith equation in j variable xj. This is the question, but this question is wrong. So full credit for students for attending the question. Consider a system of linear equations ax equal to b. A equal to eij n by n square matrix, a real square matrix, and b equal to the column vector b1, b2, bn. Will transpose t, that means is the column vector, and x equal to x1, x2, xn will transpose, that is the column vector, and kth iteration is x vector equal to x1 k, x2 k, xn k will transpose be the solution vector obtained at the kth iteration, and xi is the column vector xi1, xi2, xin. This whole transpose be the exact solution of the system 1. The error vector epsilon k, that is the uh, error at the kth iteration, epsilon 1k, epsilon 2k, epsilon nk whole transpose, where epsilon ik equal to xi minus xik, I equal to 1 to n. The error difference ek equal to xk plus 1 minus xk. This notation k for k iteration, so xk plus 1 is the for the k plus 1 iteration equal to x epsilon k minus epsilon k minus 1. This is the epsilon I, this is the error term, and this is the error difference. So E is the error difference here, and eik equal to xik plus 1 minus xik. So this is the clearly a k plus 1 approximation for the Gauss-Seidel iteration is given by xik plus 1 iteration equal to 1 by aii bracket bi minus summation over j equal to 1 to I minus 1 aij xg k plus 1 iteration minus summation over j equal to I plus 1 to n aij xj k bracket close. I runs from 1 to n and k equal to 0, 1, 2, and also the iteration number k. Let this capital M is equal to maximum over I is the 1 by aii modulus of aii summation over j equal to 1 to n j not equal to I modulus of aij, and let mi equal to 1 by aii summation over j equal to 1 to I minus 1 modulus of aij, I equal to 1 to n. Clearly 0 less than equal to mi less than equal to m less than 1. Now, epsilon I k plus 1 in the iteration is equals to modulus of xi I minus xi k plus 1 in the iteration. This equals to xi I, actually this is the value, and xi k plus 1, already xi k plus 1 from 4, we get this, and xi I is the exact solution. So put the solution in the equation, this aii bi minus summation j equal to 1 to n aij g hij, and this modulus of epsilon I k plus 1 equal to modulus of this. So this less than equal to 1 by modulus of aii, this modulus summation modulus of aij modulus of epsilon j k plus 1. This is the epsilon j for k plus 1 iteration, plus modulus of aij modulus of, this is the modulus of epsilon jk. This less than equal to is 1 by modulus of aii summation j equal to 1 to I minus 1 modulus of aij norm of epsilon k plus 1, and plus this is the summation over j equal to I plus 1 to n modulus of aij norm of epsilon k. So this is equal to mi by the definition of mi, and is equal to m minus mi into norm of epsilon k. Therefore, norm of epsilon k plus 1, because this is the epsilon I k plus 1 equal to this, so this is the norm of epsilon at that duration k plus 1 duration less than equal to mi, norm of epsilon k plus 1 duration plus m minus mi, this norm of epsilon k duration. So norm of epsilon k plus 1 duration less than equal to m minus mi by 1 minus mi norm of epsilon k. Since 0 less than equal to mi less than equal to m less than 1, then m minus mi by 1 minus mi less than equal to m. And from above, we get, obviously from this relation, we get norm of epsilon k plus 1 less than equal to m norm of epsilon k. And this shows that the rate of convergence of the Gauss-Seidel iteration is also linear. And the successive substitutions give, so from this, norm of epsilon k less than equal to m epsilon norm of epsilon k minus 1. And again, for epsilon k plus 1, k minus 1, we get m into epsilon k norm of epsilon k minus 2, and so on, so on, so on. So m into m, k factors, norm of epsilon 0 is the iteration. So we get norm of epsilon k less than equal to m to the power k norm of epsilon 0. Now, if m is less than 1, then norm of epsilon k tends to 0 as k tends to infinity. So this m to the power k, so this tends to 0. So this m is less than 1. So m to the power k tends to 0 as k tends to infinity. The sequence xk is sure to converge when m is less than 1. That is summation. M means this expression of m is this equation 5, this maximum I over the 1 by ai less than I equal to 1 to 1 over bij. So this less than 1. So this means this less than norm of ai. Summation over j equal to 1 to n, j not equal to I, not mod of aij less than not is mod of aij for I. M is less than 1, that is m is less than 1. Actually here m is this, so this is less than 1. So this is not one mod of aii. Actually this is the wrong, actually aii. This expression is aii. Mod of aii, not aia, aii. Correct this. In other words, the sufficient condition for Gauss-Seidel's iteration is that the coefficient matrix is diagonally dominant. Now from 7, norm of epsilon k plus 1 less than m norm of epsilon k. So this is equals to m norm of epsilon k plus ek norm of ek plus epsilon k plus 1. And ek, error difference ek is the epsilon k minus 1. So get less than equal to m norm of ek plus m norm of epsilon k plus 1. So 1 minus m norm of epsilon k plus 1 less than equal to m norm of ek. Hence norm of epsilon k plus 1 less than equal to m by 1 minus m norm of epsilon ek. And but the question paper here, this is the question paper. Xi minus xk plus 1 less than equal to m by m minus 1 norm of xi minus xk. Actually, xi minus xk, this is the xi minus xk is the this is the xi minus xk is the epsilon. So actually, xi minus xk is the epsilon, and xi minus xk is epsilon. This is wrong. Actually, this is the ek. Ek means this xk minus xk plus 1. Already error difference we define here. This is the ek is the xk plus 1 minus xk. Value of x at the k plus 1 iteration minus value of x at the k iteration. So ek is the error difference between two values, but epsilon is the error difference, the exact value minus k iteration value of x at the k iteration, and xi is the exact value. So this is the error difference, and this is the ek is the error difference at the k iteration, and xi epsilon is the error at the k iteration. And the extra, this relation gives the absolute error at the k plus 1 iteration in terms of the error difference at k iteration and k plus 1 iteration. Also, this is the extra. Norm of epsilon k equal to xi minus xk. So we can write this less than equal to this norm plus this norm. So this equals to norm of epsilon k plus 1 plus norm of epsilon k. So we can write this norm of epsilon k less than equal to m to the power k by 1 minus m norm of epsilon e0. That is the norm of xi minus xk. Actually, this is the bracket, not power, the iteration for k iteration xk less than equal to mk by 1 minus m norm of x1 minus x0. And note that this is the vertical line. In this vertical line, if the coefficient matrix is strictly diagonally dominant, then the iteration method converges. If the coefficient matrix is strictly diagonally dominant, then the method converges. But if the iteration converges, then the coefficient matrix may not be diagonally dominant. So this condition is sufficient condition, not necessary for this. Next question 13. If it is given that lambda 1 equal to 6 is the largest eigenvalue, and x1 equals to 1 minus 5 minus 0.5 is the corresponding eigenvector of A, find the next dominant eigenpair of A. But this question is out of syllabus. Actually, if you're interested for this, find the next largest eigenvalue, this Wayland method, and searching the website Wayland method is the for this method. Next question 14. So that the matrix E 0 1 1 1 do not have LU decomposition, and suppose LU decomposition of the matrix A equal to Aij n by n exists, then determine the n square equations in n square unknowns to express A equal to LU by Crowd's reduction method. If ux equal to y for x vector, this is the actually X matrix, column matrix, x1, x2, xn, whole transpose, and Y is the column vector, is y1, y2, yn, whole transpose. Then discuss how to solve Ly equal to B. Now first, this is the A is the Aij, n by n real matrix, square matrix of order n, and delta 1, delta 2 are the principal minors. So delta 1 is the first order principal minor, delta 2 the second order principal minor, a1 1, a1 2, a2 1, a2 2 is the determinant, and delta 3, and so delta n is actually the determinant of this, are n leading principal minors of the matrix A. The LU decomposition of A exists if and only if these all leading principal minors are not equal to 0. But here E is equal to 0, 1, 1, 1. So delta 1 is 0 and delta 2 is the determinant, this minus 1 not equal to 0. But since this delta 1 equal to 0, so all leading principal minors not equal to 0. So LU decomposition is not possible for this case. Note, the LU decomposition for a matrix exists if and only if it can be reduced to row reduced Euclidean form without any row interchange. So, LU decomposition of a matrix exists if and only this. It means the matrix can be reduced to row reduced Euclidean form without any interchange, the row interchange. Then LU decomposition for a matrix exists. The more general theory this. Now second part, this A is the A by A matrix square order n equal to LU. L is the lower triangular matrix, U is the upper triangular matrix. Let L is the this lower triangular matrix, this principal diagonal is this, and above the principal diagonal all elements are 0, and U is the lower triangular matrix, and this principal diagonal are 1, and below the principal diagonal are all elements are 0. And total number of Lij is this. Here first row 1 element, these 2 elements, and this is the n elements. So 1 plus 2 plus n. So total number of Lij and number of elements Lij is n into n plus 1 by 2. And similarly, total number of Uij is this. Here in this n minus 1th row is 1. N minus 2th row is 2, and the first row is this n minus 1. So 1 plus 2 plus n minus 1. So the total number of Uij is this n into n minus 1 by 2. So total number of unknowns, that is the Lij and Uij, small Lij and small Uij, equal to n square by 2 plus n by 2 plus n square by 2 minus n by 2, that is equal to n square. Total number of unknowns is n square. Then LU equal to gives the following steps, matrix multiplication. First, we multiply all rows of L by the first column of U. All rows of L by the first column of U. So matrix multiplication LU. All rows, this first row, this first column. First row, second row, first column. So this first row, first column. So first row, first column, L11. So L11 equal to and the matrix capital A, so equating this, so A11, so L11, so this equals to this, and for the second row this, and for the first column this, so L21 into 1, L22 into 0, so actually this L21 equal to A21, so all rows of the L matrix, dot triangular matrix, multiplying with the first column of the U, then we get this Li1 equal to Ai1, I equal to 1 to n. So we get here n equations. So this is the n equations, we get this. And multiplying next, and actually Li1, this is the, we find this A1, L11, L21. Actually by these n equations, we can find the first column of the L matrix, capital L matrix. So by these n equations, we can find this L11, L21, L31, Ln1. Next, multiplying the first row of L by all the columns except the first column of U. multiplying the first row of L by all columns except the first column. So this uh, first row of L, this, and this second column, multiplying the first column with the first row with the second column. So L11 into U12 equal to this into this. We can find this A12, actually A12. So we get U1j equal to A1j by L11. So first row with second row, the second column, third column, first row, third column. So A13, first row, fourth column, this A14, multiplying this and adding this. So we get j equal to 2, 3 up to n. So here we find this n minus 1 equations here. And thus the first row, actually this U12, U13, so we get the first row by this n minus 1 equations, we get first row of the U matrix, this. Next, multiplying second to nth row of L by the second column of the U. Similarly, second row to nth row, first second row to second column, and third row to second column into second column, fourth row into second column, we get these equations for I equal to 2 to 3 to n, actually n minus 1 equations from this. And thus the second column of L is obtained. Multiplying second row of L by the third to nth column of U, and we get U2j equal to this, j equal to 3, 4 to n. We get here n minus 2 equations, and the second row of U is obtained. And in this way, we find two general formulas actually for rth column, to determine the rth column of L. We LIR equal to AIR minus summation k equal to 1 to r minus 1. LIK UKR, r is less than equal to I. Actually, r runs from 2, 3 to n. If r equal to 1, then this k equal to 1 to 0. So these all terms vanish. So actually I1 equal to AI1. Actually, when r equal to 1 in the equation 1, actually we get the this case for r equal to 1. And for r equal to 2, so r equal to 2, so I is greater than 2. So 2 is less than equal to I. I is the this I 2 less than equal to I. So LI2 equal to AI2 minus k equal to 1 to 1. So actually for r equal to 2, we get this equation is this. Actually we get this equation. So r equal to 2, equation 1, put r equal to 2, we get these equations from these equations. And total number of equations for r equal to 1, we get in equations ith case. This r equal to 2, n minus 1 equations, already get these n minus 1 equations. So r equal to 3, n minus 2 equations. So r equal to n, we get only 1 equation. So we get total number of equations, actually n square by 2 plus n by 2 equations. And similarly for the rth row, if to find the rth row of U, URJ equal to ARJ minus summation k equal to 1 to r minus 1, LRK UKJ whole divided by LRR. R is less than J. R equal to 2, 3 to up to n. When actually r equal to 1, so these terms vanish. So we get U1j equal to A1j divided by L11, r equal to 1. So we get r equal to 1, and this equation, this r equal to 1 for r equal to 1 in equation 2. This second case, this r equal to 1. We get actually n minus 1 equations for r equal to 1. Yeah, so we get r equal to 1, we get n minus 1 equations. And when r equal to 2, so 2 is less than j. So j is greater than 2. greater than 2. So j runs from 3, 4, 5. When r equal to 2, j equal to 3, 4, 5, and so on. So when r equal to 2, we get u to j, a to j, and k equal to 1 to r minus 1, 2 minus 1. So k equal to 1. So r 1, 1, l 1, 1, u 1, j whole divided by l 1, 1. Actually, we get this equation, this equation, j equal to 3 to 4 to up to n. So r equal to 2, we find these equations, these n minus 2 equations for r equal to 2. Actually, this we get for r equal to 2, we get n minus 2 equations, and and so on. Plus when r equal to n, and we get only one equation, and so adding all these, we get n square by 2 minus n by 2. Hence, the total number of equations to find n square unknowns Lij and Uij is equal to this n square. So, total number of equations is n square, and total number of unknowns is also n square. Next, third part of this question. If ux equal to y for x equal to this and y equal to this, then discuss how to solve Ly equal to b. And now the system Ax equal to b, and then a equal to Lu. So we can write Lux equal to b. And set this ux equal to y, where y is the column vector y1, y2, yn, and x is the column vector x1, x2, xn. So Lux equal to b implies Ly equal to b. That is, L is the lower triangular matrix. Already we find this, and y is this column vector, and b is this b1, b2, bn column vector. The unknowns y1, y2, yn can be determined by the forward substitution, this y1. So multiply this into this, first row this column, second row into this column equal to this element. So we get y1 equal to b1 by L11, and yi equal to bi minus summation t equal to 1 to I minus 1 lik yk divided by lii, I equal to 2, 3, n. So we find all y, y1, y2, yn. So this, all find this. Now ux equals to y gives, u is the upper triangular matrix is this, and x equal to x1, x2, xn, and y already find this y1, y2, yn. So the value of x1, x2, xn can be determined by the back substitution. This first row, this column, second row, this column. So first row, this column equal to y1, second row, this column equal to y2. So we get the back substitution with this yxn equal to yn, and xi equal to yi minus summation over k equal to I plus 1 to n uik xk, I equal to n minus 1, n minus 2, and dot 2 into 2, 1 up to this. Next question, 15. Write down the basic assumptions for finding the dominant eigenvalue of a real matrix A n by n by power method. How to convert the rate of convergence. Rate of the method depends upon the magnitude of its eigenvalues and state when the method fails. Basic assumptions for power method. Let A be an n by n non-singular real valued matrix, and lambda 1, lambda 2, lambda n are eigenvalues with corresponding eigenvectors x1, x2, xn. Assumptions for power method is this. This modulus of lambda 1 greater than modulus of lambda 2. Note that this sign is greater than sign, not greater than equal to. Greater than equal to dot 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 greater than equal to modulus of lambda n greater than 0. Lambda 1 is real eigenvalue with the largest magnitude. And second assumption is this: x1, x2, xn are n linearly independent eigenvectors, even though some of the eigenvalues lambda 2, lambda 3, lambda n may not be distinct. Now this power method is this: any given eigenvector x in the space of eigenvectors x1, x2, xn can be written as x equal to c1, x1 plus c2, x2 plus cn, xn, where ci are constants with c1 not equal to 0. And from the definition of eigenvector, axi equal to lambda xi, I equal to 1 to n. Pre-multiplying by a on both sides of 1 and using 2, we get ax equal to c1 lambda 1 x1 plus dot 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 plus cn lambda n xn. Again pre-multiplying a, we get a square x equal to c1 lambda 1 lambda square x1 c2 lambda 2 lambda 2 square x2 and so on. And taking common lambda 1 square, we find this. And in this way, we get a to the power k x lambda 1 k c1 x1 bracket c1 x1 plus c2 lambda 2 by lambda 1 whole to the power k x2 and plus 1. And next step, again multiplying both sides by ak plus 1 x equals to this equation 4. Since lambda I by lambda 1 modulus is less than 1 for j I equal to 2, 3 to n. So lambda I by lambda 1 whole to the power k tends to 0 because this modulus is 1 as k tends to infinity, and lambda I by lambda 1 whole to the power k plus 1 is also tends to 0 as k tends to infinity. Hence from 3 and 4 we get this akx approximately equal to lambda 1 to the power k c1 x1, a to the power k plus 1 approximately equal to lambda 1 k plus 1 c1 x1 as k tends to infinity. The main trouble is that lambda 1 to the power k either grows exponentially or decay to 0 at k tends to infinity. To avoid this, the eigenvalue lambda 1 can be obtained as the ratio of the corresponding components of a to the power k plus 1 x plus and a to the power kx as this. So lambda 1 can be determined equal to the limit k tends to infinity a k to the power a to the power k plus 1 x, this is the rth component, and a to the power kx the rth component. This r is equal to 1 to n, where the suffix r denotes the rth component of the vector. The iteration is stopped when the magnitude of the differences of the ratios are less than or the given tolerance level. The convergence of this method is linear. The rate depends on the size of lambda 1 relative to the next largest eigenvalue lambda 2. If modulus of lambda 2 is less than equal to modulus of lambda 1, then the faster convergence is obtained. But the convergence is linear convergence is this. So we get a number of iterations, large number of iterations up to 100, 125 and so on. In order to keep the round of error in control, we normalize such that the largest element is unity, the vector before the pre-multiplying a. So in practical, we can write the method as follows. Let x0 is the first iteration, 0th iteration, initial with a non-zero arbitrary initial vector, which must be non-orthogonal to the vector x1, and find the k plus 1th iteration, this y k plus 1th iteration equal to a x kth iteration, and x k plus 1th iteration equal to y k plus 1 by m k plus 1. This is the not is power, is the power in this k plus 1 means the k plus 1th iteration. This is the iteration k equal to 0, 1, 2 and so on, where m k plus 1th iteration is the largest element in the magnitude of y in the k plus 1th iteration. Then the largest eigenvalue is given by lambda 1 equal to limit k tends to infinity m at the k iteration. And the corresponding eigenvector is the x1 equal to limit k tends to infinity x k plus 1 iteration. Now, power method fail when the matrix A is not diagonalizable, that is when the number of linearly independent eigenvectors is less than n. Number 2, this matrix A does not have a dominant eigenvalue, or when lambda 1 greater than lambda 2, but modulus of lambda 1 equal to modulus of lambda 2. That is example 2 is greater than minus 2, but modulus of 2 equal to modulus of minus 2. So this is the does not have dominant eigenvalue, numerically dominant eigenvalue. And when a to the power k will have a significant round of error in their entries, so power method, then the power method fails. Or the initial approximation x0 is orthogonal to x1, then power method may fail. Next question, 16, unit 6, differential equation, ordinary differential equation. Deduce Euler's method to solve the initial value problem y dash, that is dy dx, equal to fxy with the initial condition yx0 equal to y0 using Taylor's series expansion. Does this method always converge? Justify your answer. Euler's method is a single step method for solving first order differential equation. In the syllabus only first order differential equation. This dy dx equal to fxy with yx0 equal to y0. We have to find the approximate values y at equally spaced points x0, x1 up to xn, where h equal to step length equal to b minus a by n. Let yi equal to yxi. Xi is the x0 plus I equal to 0, 1 to n. Now y1 equal to y x0 plus h, approximately equal to yx0 plus h, y dash x0 plus order of h square, expanding by Taylor's series expansion about x0. Neglecting the terms order of h square and higher order due to the small h, we have y1 approximately equal to y0 plus h into y0 dash. Actually, y0 dash means dy dx at x0. Dy dx means this dy dx equal to fxy. So actually we this fx0 y0. So y0 plus h f of x0 y0. Similarly, y2 approximately equal to y1 plus h fx1 y1. And this is the iteration formula yi plus 1 approximately equal to yi plus h fxi yi equal to 0, 1 to n minus 1. Second part, the convergence analysis. Actually, this is the out of syllabus question. This is the convergence analysis for Euler's method is the out of syllabus question. But we discuss here basic preliminary ideas here. It is clear that an error is induced at every step due to the truncation of the Taylor series. This is referred to as the local truncation error, LTE, of the method. For Euler's method, the local truncation error is order of h square. Hence, this method is referred to as the first order technique. So, we apply here first order technique. The global error is defined as the absolute value of the difference between the true solution and the computed solution. If we neglect round of error, it is reasonable to assume that the global error at the nth step is n times the local truncation error, since n is proportional to 1 by h. So, global error is proportional to LTE by h. And this implies that for the kth order method, the global error scales as h to the power k. So here Euler's method is the first order method. So global error scales as h. A convergent numerical method is the one where the numerically computed solution approaches the exact solution as the step size approaches to 0. That is, limit h tends to 0, step length, norm of ei. Ei is the this y cap. This means the actually the exact value at the xi minus this computed value yi at the point xi, and this is the ei. When this error equal to 0. And now if fxy is continuous in x and y and satisfies the Lipschitz condition with respect to y, and y is sufficiently smooth, then the Euler's method converges. But it is very slow procedure and this not stable, but this convergent. Next question, 17. Actually, this practical question. Solve the dy dx equal to x square plus y square y and 0 equal to 1 by fourth order Runge-Kutta method from x equal to 0 to x equal to 0.2 with step length h equal to 0.1. Actually, the computational scheme is this k equal to 1 by 6. Already we have done in the practical. This k1 is this, k2 and is this, k3 and is this, k4 and is this, and this table is this x0, y0, fx0, and this h, fx0, k0, k1 this. For the 0 means the k0 is the iteration, x0 plus h by 2, y0 plus k1 by 2. Actually, this is the k1 0. This is the k1 0, and this is the k2 0. This is the k3 0, and this is the k4 0. And this k4 0 and k0 is the actually the sum of this column, this 1 by 6 times and cj ki. Actually, cj means here the cj is 1, C1 is 1, C2 is 2, C3 is 2, and C4 is 1. This Cj into Ki1. And y1 equal to y0 plus k0. K0 means the 1 by 6 summation of this column of this summation of this and so on. Actually, this scheme is by this scheme we find this the table a n x n y n f x n h f x n y n c j p I. This is the x0 0 initial step. This y1. This is the f x n. This is the x square plus y square. H into f x n and cj. This here is cj is 1 and this 2 and c3 is 2 and c4 is 1. And the sum of these columns and whole divided by 6, we get k0 and we get the y at the point 0.1 is this and y at the point 0.2 is this is the answer for the Portocarrero method. Thank you for watching this video.